So, ladies and gentlemen, what I want to do now is I want to take you through the assignment problem. The assignment problem is a pure balanced transportation problem. Full stop. It's a pure balanced transportation, okay, where the total supply and the total demand are equal to 1. The total supply is 1, the total demand is 1. Now, there are practical situations where this can happen, because their goal is to determine the efficient assignment of people. You're assigning people to projects. You can't assign 2 people to a project. For example, if you have a football match, you can't assign 2 referees practically to be on the pitch, in the center of the pitch, controlling the game. It's not done. It got to be 1. So each stadium during the Premier League will be assigned 1 center referee. Full stop. Assignment. That's it. That's an assignment problem. Okay. For example, you want to assign some salesperson to some territories. No more than 1 person will go into 1 territory. Auditors to company. You have 1 auditors, 1 company. You want to assign contracts to bidders. You can't say that 2 people are bidding and both of them should take the contract. No, only 1 guy to take the contract. Only 1 team of officials to 1 soccer game. And so we have an M by M assignment problem. And this was developed by a man known as Kuhn. Okay, Kuhn. We call it the Kuhn's Hungarian method. And we use that Hungarian method to solve the whole of the assignment problem. It's a very simple thing. Let's take a typical example. Very quick typical example. At the Atlantic Coast Conference, they have these basketball games. They have 4 basket games on a particular night. And the conference office, okay, they want to assign 4 teams of officials. So 4 teams of officials to the 4 games. And the games are in different towns in such a way that they will minimize the total distance traveled by the officials. Now, the distances those officials will travel, which are in miles, to the game, the location, are all shown here. So if you look at it, the officials A here, okay, they will have to travel from here, okay, and then they will have to now travel the distance of 210 to Raleigh, 90 to Atlanta, Durham, 180 to Durham, Clemson to, 160 to Clemson. Now, straight away, if you look at the distance, because you want the shortest distance, all right? So the temptation will be that, official A will have to choose what? Atlanta. Boom. Okay. And so because you believe that official A will have to choose Atlanta, you just select that, and that's it. Official A will choose Atlanta. Okay, that's true, but hold on. Let's look at the group of officials in B. If you look at them, they also have to travel those very distances, and they too will choose what? Atlanta. Okay, they too will choose Atlanta. Now you have a problem. You can't assign 2 groups of officials to Atlanta. Now, if you look at C, okay, if you look at C, they too will choose Atlanta. So it's not straightforward like that. And then D, they too will choose what? Atlanta. So you got to do things in a very, very, logical, systematic, methodological way, other than just selecting according to numbers. And there will be that temptation that, since this guy has chosen Atlanta already, A, and this B cannot choose Atlanta, then you should choose what? You should choose this one, okay, Raleigh. Another temptation. And because this guy has chosen that this one cannot choose that, the next shorter one is that this one should choose what? Durham. Temptation. And then because this D officials cannot choose Atlanta, then the next shorter one is what? 80. But you see, they are going to what? Raleigh as well. Now you have B going to Raleigh, D going to Raleigh. You see, so when you use those permutations to do that, that is not, you got to use a method. So first thing, let's define the decision variables. It's a very simple thing, okay? The decision variables for this assignment problem is let X be that coach I, okay, or group of officials I as assigned to town J, okay? Let Xij be the group of coaches I assigned to town J. That is it, because they are coaches that have been assigned to the towns. Okay. The next thing is to draw the model. Well, look at the model. How many officials do we have? 4. And how many game sites do we have? 4. So how many, what do you call it? How many rounds, how many nodes are we going to have? Type it and let me see. How many nodes are we going to have? Total nodes. Total number of nodes. And total number of constraints is 8. Excellent. Is 8. Okay. So that one is very cool. So you draw them, and this is it. You draw them A, B, C, D. Okay. All of them are going to Raleigh, Atlanta, Durham, and Clemson. And then, of course, you attach the distances. So this A will be, okay, the decision variable will be XAR, where the R is the Raleigh. Okay, XBR, okay, from B to the, and then you can now have XAA for the Atlanta, but officials in A going to Atlanta. XAD for the officials in A going to Durham. XAC for the officials in A going to that. Okay, you can have this beautiful thing. Okay. So this one is very cool. Now, formulate a linear programming mathematical model for solving the problem. So formulate it. Okay. How many decision variables and constraints are there? Now, when you look at the apps, you see how many decision variables are there? How many are the decision variables? Let me see some of the answers that people have. How many are the decision variables? 4 times 4. Is that what you're saying? Yeah, 16. 16 decision variables. 16. So each one will take the cost. So 210 XA, okay, then 90 XAA, and then like that. So this is your objective function because there are 16 decision variables. So remember, we are supposed to, well, I think I made a mistake. It's not supposed to maximize, it's supposed to be minimized. So we are minimizing the distance. So this is supposed to be minimize. Okay, let me cancel that. Okay, so cancel that. And then you make it, I'm just trying to, play beautifully here to see. Okay, so you make it minimize, something like that. Okay. So that's it. Then subject to the constraint. Now, how many constraints? 8 constraints. So once again, you look at how many are leaving and how many are entering. So you do for A, do for B, do for C, do for D, do for Raleigh, Atlanta, Durham, Clemson. Okay. And you're going to use the decision variables. And all of them should be equal to what? 1. Because at the end of the day, we're expecting 1. Okay. So all of them should be equal to 1. So you should have it like this. So this is it. Okay. Each one of them, each constraint, each one of them, each constraint, each one of them, each constraint, each one of them, each constraint. And then eventually it will be 1 for each one. And then don't forget your non-negativity constraint. Okay. Many people forget that, the non-negativity constraints. We need that. Basically, that's it, formulated. Okay. Now I can put this in Excel, which I've shown here. Go through the mail of formulating this in Excel. And then I got this result. Okay. So this is the results that I had. Now the result is a very simple result. If you look at it, those are the costs that are here. Okay. Those are the costs that are there. So there's no problem when it comes to these costs. Now the final values are what you see here. The final values. And remember, the final values are the decision variables. Okay. And then the costs associated with each final, these are the reduced costs. The costs, the distances associated with each is what you have there, the distances. And then, of course, the allowable and increase and decrease for the distances are what you see on that. Okay, this is a reduced cost. And if you can remember, the reduced cost is opportunity cost of trying and forcing a final value to happen here. So You are not supposed to go to Raleigh. Okay, let me just remove that and then show you something. So if you look at Raleigh like this, you are not supposed to go to Raleigh. We are not supposed to go to Raleigh from A. A is not supposed to go to Raleigh. So if you look at the A guys, these are the A guys. And the A guys are not supposed to go to Raleigh. The only person who is supposed to go to from A is to go to Atlanta. And remember, that was the first guy that was selected. So only group A is supposed to go to Atlanta. And they will be given a value of what? 1 here. But if you force, if any of the officials, the coaches should force themselves to go to Raleigh, because the shortest distance for them is to go to Atlanta, but if they do force to go to Raleigh, then they are going to incur a huge, cost, okay, which is 90. So that is opportunity cost, okay, of going to Raleigh, forcing themselves to go to Raleigh. That is a cost that will be handled there. And you don't want that. And so that is why it's important to stick by. So each A will have to go to one group. And so if you look at each one, you have one group for each one of them. So each single one of them, okay? You have one group for each single one of them. And that is important. All right, so what we need to now do is we need to now calculate where these things are going. So now that you know that it's going to, A is going to Atlanta, okay? And that B is going to Raleigh. See that here, okay? And you have, for you to get the total minimized distance traveled, you're going to, since these ones are 1, you're going to multiply them by their respective coefficients, okay? And then C goes to Durham. And then finally, D goes to Clemson. Do you remember there was a kind of a tie? Some of our guesses came to pass, but of course, using the technologies here is more important than guesses. Okay, all right. Now, let me show you the final answer for that. So the question is, what is the optimal assignment rule? Here, and then those that had a value of 1, you show them. So for example, A had a value of going to where? Atlanta. So only this one is going to show. Okay? Only this one is going to show because A is going to Atlanta. Only that is going to show. So when you are rate drawing, you don't draw the other ones here. You just draw for the A, for just A going to Atlanta. And then you don't draw the other X. Okay. And that's what I did here. You draw it. So you first assign officials to Atlanta, officials A to Atlanta, B to Raleigh, C to Durham, and then D to Clemson. Finished. And then when you want to draw it, this is now the drawing for each one of them. Now watch it carefully. Okay? You have A going to Atlanta, B going to Raleigh. Let me just take you back to our analysis, our guesses that we did. Okay, some of them were good though. We said that A goes to Atlanta. Okay. We said B goes to Raleigh, truly. We said C goes to Atlanta, but we have to move it to Durham. Okay. And then D went to Clemson. Of course, that's what happened. Okay. So sometimes those guesses can work. And you can see that. Okay. So you can see that D went to Clemson. Okay. When C went back to Atlanta, but Atlanta has already been taken, we give it to Durham. And a balance. That is not always going to be like that. Of course. Now, in the higher level, we use a certain beautiful Hungarian approach to solve this. Anyway, once you've gotten these values, you can now find the corresponding cost. You substitute those that had a 1. Okay, give them the corresponding cost, their respective cost, multiply it, and then find the total minimum distance, which is 450. Finished. That is how you do the assignment. It's a very simple thing, but you just have to be consistent. Take your time and go through it consistently. And that will be it. A beautiful